Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Design and Manufacturing of Low-Cost SCARA Robot Rizwan LHAQ1, Umashankar KUMAR2, Naveen KUMAR3, Yash Barnanwal 4 students, Bachelor of Technology, Mechanical Engineering, National Institute of Technology, Srinagar, Kashmir Mohd. Mursaleen 1, Nazir Ahmad Sheikh 2 Professors, Department of Mechanical Engineering, National Institute of Technology, Srinagar, Kashmir Abstract. This report deals with the design and fabrication of a selective compliance articulated robot arm, SCARA. SCARA robots are among the most widely used robots in the industry due to their high accuracy and inherent rigidity. Robotics is becoming popular and has achieved great success in the last few decades, but automation isn't cheap, so everyone cannot afford to transform his unit from manual to automatic. The main objective of this project was to develop a low-cost robotic arm that can be used for pick-and-place operations. Here controlling of the robot has been done by using NEMA 17-stepper motors and Arduino Uno. This robot is having 4 DOF and can be controlled by a graphic user interface that features both forward and inverse kinematics control. By changing the program of the end-effector, this robotic arm can be used in vast applications, but mainly it can be used in the automatic assembly lines. Keywords: SCARA, robotics, fabrication, automation, Arduino, graphic user interface, GUI, kinematics, degree of freedom, DOF. Introduction: SCARA robots, developed in the early 80s, represent a breakthrough in assembly automation. Machina, 1980. The SCARA robot's performance, which included a large working area in the XY plane, a suitable height in the Z-axis, and low sensitivity for load speed, positioning, and control accuracy, allowed them to be used in electronic printed circuit assembly, as well as the automotive and home appliance industries. Robotic arms used in assembly and production processes help to eliminate human error and increase production rates. SCARA configurations are known for their fast speed, low maintenance, great repeatability, and sturdy architecture. The SCARA robot is a 4-degree of freedom manipulator. This sort of robot was created to increase the speed and repeatability of pick-and-place tasks from one spot to another, as well as to speed up and improve assembly stages. 2. Literature Review 1. Modeling, Simulation and Analysis of SCARA Robot for Deburring of Circular Components by PVS Subhashinai, N.V.S. Raju and G. Venkatarao. This research study describes the study of SCARA robot for deburring operation of circular profiles. The SCARA robot with 4 degrees of freedom is modeled in CAD software. The kinematics of robot is also explained in the simplest way. The results of joint positions and joint velocities calculated from CAD software are compared with results obtained from MATLAB. The mathematical modeling and its results in MATLAB are best explained through this paper. 2. Design and fabrication of pick-and-place robot to be used in library by Aina Sharonaki M. Kranti. The use of robots in library is becoming more popular in recent years. The trend seems to continue as long as the robotics technology meets diverse and challenging needs in educational purpose. The prototype consists of robotic arm along with grippers capable of moving in the 3 axes and an ATmega 8 microcontroller. Software such as AVR Studio is used for programming, Protesis is used for simulation, and Progisp is used for dumping the program. RFID is used for identifying the books, and it has 2 IR sensors for detecting the path. This robot is about 4 kilograms in weight, and it is capable of picking and placing a book of weight 1 kgs. 3. Robot arm control with Arduino by Abdul Latif Baba. Today, technology is developing in the same direction in line with rapidly increasing human needs. The work done to meet these needs makes life easier every day, and these studies are concentrated in robotic arm studies. Robot arms work with an outside user or by performing predetermined commands. Nowadays, the most developed field of robot arms in every field is the industry and medicine sector. Designed and realized in the project, the robot arm has the ability to move in 4-axis directions with 5 servo motors. Thanks to the holder, you can take the desired material from one place and carry it to another place, and also mix it with the material it receives. While doing this, robot control is provided by connecting to the Android application via Bluetooth module connected to Arduino Nano microcontroller. 4. Design, manufacturing, and analysis of robotic arm with SCARA configuration by Kaushik Faisal, Praveen Kumar, Akshay Rot, Ravi Ranjan Singh, Amit Nichat. This paper deals with the design of 4-axis SCARA robot. The analysis is also performed in ANSYS. For experimental setup, the robot with cardboard material is made by the author. The experimental model is used to analyze the location of motors, length of links, and its movements. The designing of the robotic arm is done in Creo software. The animation is done with various constraints in the software. This research study also includes the manufacturing and assembly processes of the robot. IJERT 10 is 060027 www.ijert.org 162. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 5. Design and Development of a 4DOF SCARA Robot for Educational Purposes by KSM Sahari and Hongwen Kia. Robotics have become a common course in a lot of higher institutions. Although there are many robots available in the market, most of them are for industrial purposes and are costly. There is a need to develop low-cost robots for students in higher institutions to learn the elements of robotics such as design, kinematics, dynamics, sensing and control. The aim of this project is to design and develop a mechanical structure of a SCARA robot that can perform certain tasks for educational, research and exhibition purposes such as pick-and-place operation. The paper discusses the steps used in design and development of a 4 degree of freedom, DOF, SCARA robot, which includes specification definition, conceptual design, product development, and testing. In specification definition phase, the specifications of the SCARA robot are first determined. After that, the best conceptual design of the SCARA robot is chosen after making concept evaluation in the conceptual design phase. Then, in third phase, which is the product generation, the chosen design of the SCARA robot is fine-tuned. Stress analysis using finite element analysis is carried out before a prototype is developed. The direct and inverse kinematics, dynamics of the robot are then modeled. Off-shelf parts are also selected based on the derived parameters from calculations. Electronic parts such as sensors and dedicated controller using low-cost microcontroller are then developed. Finally, the developed SCARA robot is tested to see whether it fits the targeted specifications. 6 Auto and manual control of robotic arm using PLC by RJAGAN1, Pirana SINGH2, CH Ashurvadam 3, K Navatha 4. The main objective of this project is to control the robotic arm manually and automatically by using programmable logic control, PLC, to pick the moving object on a conveyor belt. In industries, highly advanced robots are used, but still the controlling is done by manually or processors like Arduino, microprocessors, etc. There are several disadvantages by using these processors, like microcontrollers cannot work in the environments with the high levels of vibrations, corrosion, humidity, and other environmental factors. All these problems are overcome by using programmable logic controller, PLC, which acts as a brain to control the robotic arm. This project focuses to create and build more compact, useful, and cheaper robotic arm to perform various functions where human is proven too dangerous to perform a specific task, and also to eliminate human errors to get more precise work. 7. Review on Development of Industrial Robotic Arm by Rahul Gautam 1, Ankush Gedam 2, Ashish Zade 3, Ajay Mahawedewar 4. The use of industrial robots is increasing in areas such as food, consumer goods, wood, plastics, and electronics, but is still mostly concentrated in the automotive industry. The aim of this project has been to develop a concept of a lightweight robot using lightweight materials such as aluminum and carbon fiber together with a newly developed stepper motor prototype. The wrist also needs to be constructed for cabling to run through on the inside. It is expensive to change cables, and therefore the designing to reduce the friction on cable is crucial to increase time between maintenance. A concept generation was performed based on the function analysis, the specifications of requirements that had been established. From the concept generation, 24 sustainable concepts divided into 4 groups, representing an individual part of the whole concept, were evaluated. 3. Methodology. Figure 1. Rough model 4. Design of robotic arm. Figure 2. Assembly in SolidWorks. IJERT 10 is 060027 www.ijert.org 163. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. The designing of robotic arm was done in SolidWorks. The various components part drawings are created separately, and by using these parts assembly was created. Our goal for the robot was most of the parts to be 3D printed. With the specifically built pulleys, we were able to achieve a 20:1 reduction ratio for the first joint in 2 steps. The GT2 belts we utilized here are closed loop and have lengths of 200 mm and 300 mm, respectively. 2 thrust bearings and 1 radial bearing make up the robot joints. We have a 16:1 reduction ratio for the second joint, which was produced in the same way, and a 4:1 reduction ratio for the third joint with only a single stage reduction. Because the joints are hollow, we can use them to send wires from the motors and micro switches through. There are slots on each of the belts where we may attach idler pulleys to tension them. Figure 3. Joints of robotic arm. The robot gripper is driven by an MG996R servo motor, and we can easily swap the gripper ends to get varied grasp sizes. The robot's Z-axis is powered by an 8 mm lead screw, and the entire arm assembly is supported by 4 10 mm smooth rods and linear ball bearings. The length of the smooth rods, which in this case are 40 cm, determines the robot's height. To fit in this layout, the lead screw must be 2 cm shorter, or the Z motor can be lifted by 2 cm using spacer nuts. V working the robot is controlled by 4 NEMA 17-stepper motors and has 4 degrees of freedom. It also features a small servo motor for operating the end effector, or in this example, the robot gripper. The Arduino Uno board is the brain of the SCARA robot, and it's combined with a CNC shield and 4 A4988 stepper drivers to control the motors. In terms of positioning and orientation, there are 2 approaches for controlling robots: forward and inverse kinematics. When we need to find the position and orientation of the end effector from specified joint angles, we apply forward kinematics. Inverse kinematics, on the other hand, is used to determine joint angles for a given end effector location. Here are the equations we derived for forward and inverse kinematics. Position and orientation of the end effector can be calculated by joint angles 1 and 2 mm, and the joint angles for a given position of the end effector can be calculated by X and Y6. Circuit diagram: will be using an Arduino Uno board with a CNC shield and 4 A4988 stepper motors. Even though it's a robot and appears to be more difficult, that's all the electronics we'll need for this project. It's worth noting that we could potentially use an Arduino Mega in conjunction with a RAMPS 3D printer controller board instead of an Arduino Uno. Figure 4. Circuit diagram: IJERT 10 is 060027 www.ijert.org 164. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 7. Fabrication: all the parts were printed on Creality CR10 3D printer. As previously said, the pieces are also designed to fit on a smaller 3D printer, such as the ENDER3. We utilized PLA+, the blue material, for most of the parts, as well as regular PLA for the pulleys and gripper. In the slicing software, we enabled horizontal expansion of 0.1 mm for all of them. This allows the parts to have more precise dimensions and fit better with other mechanical components such as bearings, rods, and bolts. 8. Conclusion: a SCARA manipulator with 4 degrees of freedom was created, and it now serves as a platform for testing and studying a variety of control approaches. The parts designed were made available to the online audience so that anyone can 3D print and apply SCARA in actual form for further testing of strength, efficiency, economic viability, and use in many industrial domains. The morphology chosen for the robot's design and execution allowed it to do a variety of demonstrations and activities, which were easily and quickly programmed using an intuitive graphic interface built specifically for that purpose. The built robotic arm may be used in a variety of ways, and any type of end effector can be attached to the robot for various purposes. For example, we can attach a 3D printer hot end to the robot to turn it into a 3D printer, or attach a laser head to turn it into a laser cutter. 9. Specifications: 1. Degree of freedom, 4.2. Payload capacity, fully extended 200-250 gm3. Maximum reach, fully extended 550 cm 4. Rated speed, adjustable 0 to 80 rpm 5. Hardware interface, USB 6. Control software, computer interface, GUI, 7. Arm 1 spin, 180 degrees 8. Arm 2 spin, 180 degrees 9. Arm 3 spin, 180 degrees 10. Gripper opening, adjustable X. References: 1 KSM Sahari and Hongwen Kier, Design and Development of a 4DOF SCARA Robot for Educational Purposes, article in Journal Technology January 2011. 2 Alirazakaili Ahmad Dumlu, M. Fadekorases and Koksal Aaron Turk, Detailed Analysis of SCARA Type Serial Manipulator on a Moving Base with LabVIEW, article in International Journal of Advanced Robotic Systems February 19, 2013. 3 Kurt E. Clothier and Ying Shang, A Geometric Approach for Robotic Arm Kinematics with Hardware Design, Electrical Design, and Implementation, Journal of Robotics August 18, 2010. 4 Bernhard Moll and Oscar von Streich, Design and Application of a 3DOF Bionic Robot Arm, January 2005. 5 Dr. Amar Nageshwar Rao, Jeevan, Modeling and Analysis of Robotic Arm Using ANSYS, International Journal of Scientific Engineering and Technology Research, Volume 04 Issue .33, August 2015. 6 Arjigan, P. Rana Singh, Ch. Ashurvadam, K. Navatha Auto and Manual Control of Robotic Arm Using PLC, Volume 6, Issue 8, August 2017. 7 Ali Medjaburi and Lamine Mehanewi, Active Disturbance Rejection Control of a SCARA Robot Arm Volume 8, Number 1, 2015, 8 Ashley Baby, Chinu Augustine, Chinu Tampi, Maria George, Abhilash AP, Philip C. Jose Pick and Place Robotic Arm Implementation Using Arduino Volume 12, Issue 2 VER3, March-April 2017. 9 Aina Sharananki, M. Kranthai Design and Fabrication of Pick and Place Robot to be used in Library Volume 4, Issue 6, June 2015. 10. Rahul Gautam, Ankush Geetam, Ashish Zaid, Ajay Mahawedewar, Review on Development of Industrial Robotic Arm Volume 04 Issue 03 Mar-2017. 11. Abdel Latif Baba Robot Arm Control with Arduino Technical Report June 2017. 12. KSM Sahari and Hongwen Kier, Design and Development of a 4DOF SCARA Robot for Educational Purposes, article in Journal Technology January 2011. 13. MD Anasur Rahman, Alimal Haq Khan, Dr. Tofail Ahmed, MD Mohsin Sajid, Design, Analysis, and Implementation of a Robotic Arm The Animator Volume 02, Issue 10, 2013. IJERT 10 is 060027 www.ijert.org 165. This work is licensed under a Creative Commons Attribution 4.0 International License.